doing part C. Let's see how it goes. This is nice. This is nice. Um, at what domains does C appear to be differentiable? Differentiable? What part? Every part excluding this zero, okay? So we can say from -1 less than or equal to x, we are including -1 because you see this shaded dot, so we are including it. But we are not including 0 because there's a point at 0. And then we can say that we are not including 0, okay, just after 0 and all the way to 2. So you say this and this. These are the intervals or points where we have this not being. If they say points, I guess maybe they want us to state. I'm not sure. But yes, you can, any point within this range. That's why I had to put it this way. Okay? Because we can't just put the whole numbers, because also these are the points. These in-between points are also, at this point, it's also differentiable. It's differentiable at this point. It's differentiable at this point. All right. So that is what it is. Now let's see part I. And why is the reason? What is the reason? Why is it differentiable? It is differentiable at all these points because there is no V. There is no cusp or sharp point. So you can say where does it appear to be differentiable? We've put there because you can say there are no cusps. There is no, so you can say function is continuous. You can say function or y equal to f of x. Y equal to f of x is continuous. It just means the function is continuous at the points, and has no sharp corners, or cusps at the points, okay? At the points which we have included in the interval, okay? It is continuous all the way from here to the x. We are not counting this, and it is also continuous all this way. But here at exactly this thing here, we have a cusp, so it won't be differentiable. So remember, for it to be differentiable, 1, it must be continuous, and 2, it should have no sharp corner or cusp. So that is the point which we took. Those are the points. Now part II says continuous but not differentiable, and that is at x equal to 0. Here it is continuous, but it's not differentiable because it has a cusp, okay? It has a cusp. So you can say, now what is the reason? You can say function is continuous. Why is it continuous? Function is continuous, and you can say why, because there is no hole, jump, or vertical asymptote at the point, okay? And now you can say, but it is not differentiable, okay? Let's put why it is not differentiable. So you can say function is not, or y is equal to f of x, that's the other thing you can say, is not differentiable at x equal to 0, because as there is a cusp at the point, okay? There is a cusp or a V shape at this point, so it is not differentiable. Now let's do the C3 now. Is there a point where it is neither continuous nor differentiable? You can say no such point. Where it is neither continuous nor differentiable, there is no such point. Why? You can say here that the function is continuous. Function is continuous throughout the whole domain. Function is continuous throughout the domain, okay? Throughout the domain, which is, you can put to 0 to say from -1 less than or equal to x less than or equal to 2. It is continuous throughout the whole domain, okay? Why? As there is no hole, jump, or vertical asymptote. Vertical asymptote. Okay, so here it is. That is it. Function, so there is no point where it is neither continuous, okay, nor differentiable. So in other words, if they say neither continuous nor differentiable, it means it is not continuous and it is not differentiable. There is no such point because function is continuous everywhere. So there is no point where it is not continuous and not differentiable. There is no such point because it's continuous everywhere, okay? So they say both neither continuous nor differentiable. It means both of them should be both. It should be not continuous and it should be not differentiable. But we've just proved that it is continuous everywhere. So you will never find a point where it is not continuous and not differentiable. Now we can go to do part D. Is the last question. Goodbye for now. See you when we do it.